Welcome to Orgo 1, Lesson 14. We're talking about acids and bases. And we talked about an Arrhenius acid. Like, I shouldn't give this chart, that Arrhenius said that an acid is anything that increases H3O plus concentration. And a base is anything that increases OH minus concentration. But that was very limited in scope. That was like you could say NH3 is therefore a base because you put it in H2O and it dissociates and gives you NH4 plus and OH minus. Or rather, it associates and gives you NH4 plus and OH minus. But what if it wasn't in water? See, like the NH3 itself, in itself, doesn't have OH minus. You know what I mean? It just helps to do a reaction that creates OH minus. And HCl, when you react that with H2O, fully dissociates and makes H3O plus and Cl minus. And that's great because, see, so that's an acid because it leads to more H3O plus. That's a base because it leads to more OH minus. But what happens when I react the two of them together? If this is an acid in this reaction and that's a base in that reaction, then reacting HCl with NH3 should be considered an acid-base reaction. Do you follow the logic of this? And if it should be considered an acid-base reaction, who's the acid and who's the base? I don't see any H3O plus and I don't see any OH minus. So along come Bronsted and Lowry and say, you know what? We're looking at it the wrong way. It isn't that HCl creates H3O plus. It's just because there's water there and the water becomes H3O plus. So what's really happening is that the HCl donates a proton to the water, and Bronsted and Lowry said that an acid is a proton donor. And look, NH3 is not donating a proton, it's stealing a proton from water. And therefore, NH3, or a base, is a proton acceptor. And that's why Bronsted and Lowry are kind of more broad of a definition. So anything that's an Arrhenius acid is automatically a Bronsted and Lowry acid. But there's Bronsted and Lowry acids that are not necessarily automatically Arrhenius acids. Up here is a Bronsted-Lowry acid-base reaction. But it's not Arrhenius because there's no H3O plus and no OH minus. Do you see? What's the use of H3O plus and OH minus? Number one, we're 70% water and our Earth is 70% water. So like the protonated and deprotonated versions of water is a very useful tool. This should be our standard strong acid and strong base. Does that make sense? But walking away from that standard, we should have a more broad definition. And Bronsted and Lowry said, look, the HCl is donating the proton and so on. Well, along comes Lewis, and thank goodness for Lewis structures. And Lewis says, you're looking at this reaction all wrong. And the reason he said that is because, obviously, he looked at the Lewis structures. So how do you draw a Lewis structure of NH3? It looks like this. And how do you draw the Lewis structure of HCl? It looks like this. And how do you draw the product Lewis structures? It goes NH4 plus and it goes Cl minus. Right? And in the Bronsted and Lowry way of looking at it, this proton jumps where? Where does the proton jump from HCl? It lands on NH3, right? That's the proton donor, proton acceptor, right? But like what's actually happening? Do you notice between the reactants and the products, this bond is breaking, right? Because it's not there anymore. You don't have that bond over there anymore. And you notice there's a bond that's forming between these electrons and that H because they're not a lone pair anymore. There's a bond, right? So what's moving is maybe the electrons, maybe the protons. Did you know that a proton is 2,000 times bigger than an electron? You didn't know that? An electron is 1,800 times smaller, 2,000 we could round, 2,000 times smaller than a proton. This is why when we're calculating the mass of an atom, you don't include the electrons. Like the mass of nitrogen, there's 7 protons, the mass is 14. The 14 is protons plus neutrons. Why not plus electrons? Because even if you have 2,000 electrons, that's still like 1 proton. Do you see? It's negligible is the point. So why am I saying that? Why am I making the point there? You could either say that the electrons are moving to grab the proton, or the proton is moving to grab the electron, which, okay, so here's an interesting physics idea. Here's the Earth. And let's say 10 feet above the Earth is me. Me. Right? I let go of both of those things. Right? You could either say that I fall towards the Earth, or you could say that the Earth falls towards me. Which one's the more like obvious? Because both are happening, right? If you learn physics, when I jump up right now, I move the whole Earth. I did. It's just I move the Earth like a microscopic, negligible amount compared to how much I move myself, right? I'm going to have a force of attraction with the Earth. But because my mass is so small, my speed will be much bigger. The Earth's mass is so big, its speed will be much smaller. So do you see, we shouldn't be talking about the Earth went to me. We should say that I went to the Earth. And we shouldn't say that the proton, 2,000 times bigger, jumped onto the electrons. We should say that the electrons much more easily moved towards the proton, right? If you know resonance, if I taught you resonance, if you understand resonance, what did we move in resonance? What was moving? Dots and sticks. We didn't move atoms, we didn't move charges. The charges ended up being recalculated. But what did we physically push? What do our arrows mean? Curved arrows was electron flows. And we did that so we could understand how to push arrows in mechanisms. So this will be our first mechanism. We're making a bond between that nitrogen and that hydrogen using those electrons. Look. If I showed you this, for example. As a before. And then I showed you this as after. Could you figure out what happened? Could you realize that, like, look, there's 3 pairs right here. Here's 2 pairs and a bond. One of the pairs must have went and made a bond, right? Do you see, like, that? You could look at before and after. There's a lone pair right there. There's not a lone pair right there. It's a bond. The lone pair must have made a bond. To who? To the hydrogen. How many bonds can hydrogen make? 1. Just like over here, this carbon can't pick up new electrons unless it loses electrons. The hydrogen can't pick up new electrons unless it loses electrons. It's just this is inside the same molecule and this is between 2 molecules. Do you see the parallel? Do you see the parallel? Do you see what those arrow push say? It says that this lone pair is going to make a bond with an H. And the bond is going to go onto the Cl, and if a bond goes onto a Cl, it becomes a lone pair on the Cl. Dots become a stick, stick becomes dots. Isn't that just a simple resonance kind of an arrow push? How about this? Let's bring in chapter 1. How is this even able to happen? Here is how it's able to happen. The shape of NH3 is pyramidal. You knew that, right? And nitrogen is more electronegative than hydrogen. So you've got a vector this way, you've got a vector that way, you've got a vector that way. Towards the nitrogen, it's partial negative. Doesn't cancel out at all. The partial negatives accumulated towards the nitrogen. So the nitrogen is a negative sort of side, right? What else? HCl has 1 polar vector. And if you watch the video that I asked you to watch, then you would learn, it's free for everybody to watch, still online, it's on my channel. then you would learn that if you have only one vector, it's automatically polar, because it's not going to cancel out with anything. This thing is polar, and this side is partial positive, and this side's partial negative, right? Now think about this. If you've got a molecule that's got a negative piece right here, and you've got another molecule that has a positive piece right there, isn't the negative piece of this going to attract to the positive piece of that? Like if you just let them go, it'll just fly into it and crash into it. So these are no longer like gas molecules that are flying around the flask in straight lines just bumping off each other. This one has an attraction. It's going to line up. And here's something more fun. Here's something more fun. I hope you like it. How do we draw this thing? Chlorine is what? 1, 2, 3, 4 domains, tetrahedral, Sp3, right? So chlorine has got these kind of orbitals. Right? Tetrahedral sp orbitals with sp3 orbitals with an H right here overlapping, and it's got lone pair, lone pair, lone pair, right? Now, do you remember in chapter 1 we kind of said we're going to draw it wrong, but later we're going to have to bring it back? What do I mean by that? Carbon, for example. If I want to draw carbon's sp3 orbitals, the way we've been drawing it is like this, like this, like this, like that. But this isn't really the sp3 orbital. An sp3 means that an s and 3 different p's combined. Let's say this one is shaded, this one is shaded and shaded and shaded. This part combines and you get this big shaded region for bonding and this tiny little other side for anti-bonding. You got anti-bonding on the other side. So what's going on right here? What am I getting at? You've got chlorine with its orbitals that have lone pairs in them, bonded to hydrogen. And hydrogen's using a bonding orbital, but on the other side of that, there's an anti-bonding orbital. Just like chlorine has a bonding orbital, but on the other side is an anti-bonding orbital. Or chlorine has a bonding orbital, on the other side is an anti-bonding orbital. Why do we care about that? Look, this is not something you need to remember for an exam. Everything I'm showing you right now is just for your own personal understanding. The only thing you need to remember here is that arrow push. You need to know that when I draw a base and an acid, which way to push an arrow to get your products, this is resembling resonance. But I'm going to explain why we could make and break bonds right now. So, this is partial negative, right? And it makes sense that the negative is going to want to attract and fly into that, right? But how does that cause a bond breaking? So look, there is a bond here between hydrogen and Cl. And how do we describe that bond? You have hydrogen and you have Cl. And hydrogen has an s orbital, a 1s orbital, and Cl is using one of its sp3 orbitals. And together, these things combine to make a sigma bond, that is HCl. And what is up here on the other side? What's up there? You can't be serious. It's a sigma star anti-bonding orbital, right? Hydrogen brings in 1 electron, Cl brings in 1 electron, and therefore they have 2 electrons bonding. That's why HCl has a bond. Right? Great. But in comes this thing that we're going to call the base or the nucleophile. We're going to be calling, you might have already heard the word, nucleophile. And how can you use that word before learning acid bases? You know what the word nucleophile breaks down to? Nucleo means nucleus or positive. Phile means lover or desire. The thing that's a nucleophile wants positives. Do you see why the base wants positive? Right? It's negative, it's attracted to the positive, right? Now hear this out. HCl has a bond. It's described by this. In comes NH3's lone pairs and puts them in the opposite side of where the bond is. What's on the opposite side of a bond? The anti-bonding orbital. So imagine NH3 takes its 2 electrons and puts them up here into the antibonding orbital of HCl. How many bonds will HCl have then? 2? That's how that works? If you have 2 electrons in the antibonding and 2 electrons in the bonding, that's 2 bonds? That's 0 bonds. That's rough. You guys didn't learn chapter 1? All of my efforts, they really paid off, right? There is a bond because we counted bond order as bonding minus antibonding divided by 2. There's a bond. When NH3 takes its electrons and shoves them into the antibonding orbital, it takes its own electrons and puts 2 electrons in the antibonding. 2 minus 2 is 0. That's what causes the bond to break. Do you see when somebody else takes 2 electrons and puts them into HCl's antibonding orbital, at that moment HCl can't have a bond? So the base, putting electrons into the antibonding orbital, is what causes that bond to break. HCl is not going to dissociate on its own. It's going to dissociate because of NH3, or HCl is going to dissociate in water, but it's not going to dissociate by itself in a gas phase. Is this too much for you guys to understand? This shouldn't be too much to understand. If you can't get this, you're not going to get nucleophilic substitution. When we go to chapter 9, we're going to do the exact same thing. This is not going to look the same, but I'm going to demonstrate it is the same. In chapter 9, we might have something that looks like this. And this. And this are going to react and give us this. And how is that at all similar to what we have over here? Here's how. Pay attention. The O minus wants something positive. It's got negative, it can't resonate, it's unstable. Do you see the O minus is unstable? Nature hates charges. It just wants anything positive. Is there anything positive about this? There's a carbon-to-carbon bond, nonpolar. Carbon-to-carbon bond, nonpolar. Carbon-to-carbon, nonpolar. Carbon-to-chlorine, polar. With this being partial negative and this being partial positive. Do you hear me? So this oxygen is attracted to the partial positive. And if it starts making a bond with that partial positive, that's going to cause the bond to the Cl to break. Now here's how we can very easily take this and parallel it to what's up there. We're going to notice that hydrogen, one hydrogen, or a carbon chain can be thought of as the same thing. So just watch. If a hydrogen and a carbon chain is similar, I could just circle this entire carbon chain and pretend for a second it's a hydrogen just to see what I'm looking at. So instead of this whole carbon chain, I'm going to write this, OH minus, and instead of that, I'm just going to write H, connected to what? Cl. Does this make sense? That OH will grab an H and push off a Cl and give you H2O and Cl minus? So then this will make sense. This is not supposed to be perfectly clear for you, this nucleophilic substitution at all right now. I'm just saying this is where we're going, this is where we're at. So orgo's not memorized. There's a few memorizing things, but orgo's not memorized. To know whether this reaction happens, we use what I asked you to do from our last lesson. To know whether this reaction happens. Because look what I mean by does it happen. And we're going to parallel this thought to something from Chem 1 and Chem 2. I can show you a base right here and an acid, but then you know that the base is going to produce a conjugate acid and the acid is going to produce a conjugate base. And this is where sketchiness comes in because what if I wrote those first? What if I wrote this base and this acid? Couldn't this grab an H, push electrons off, and create from the base right here, a conjugate acid? Cl connected to an H. And from H2O's acid, couldn't I create the conjugate base, OH minus? So should a reaction matter depending on what I write first? Shouldn't the reaction happen whichever way it happens? So, and then it happens depending on what the equilibrium constant is. Look, let's make sure. It doesn't matter which one I write first. This one or this one. It's still going to go to the lowest energy, right? If I write this one first, you're going to say the reaction goes to the right. If I wrote that one first, you're going to say reaction goes to the left, right? It just goes to the lower energy side. If I write this on one side and that on the other side, or if I write that on the first side and this on the second side, no matter what, it's an acid-base reaction, but just one side of this is lower in energy. And how do you find the lowest energy side? It was the trick of pKa's. You find the acid on the left side. Which one of these is the acid? HCl. What's the pK of HCl? The answer is -5. Now, to be a good student, you should have said -5 right now because you should have practiced. But I know you just had an exam, so I'm not going to attack you for this. But by next Tuesday, you shouldn't have to flip in your book to figure out pKa, and you also shouldn't sit up between now and Tuesday memorizing the numbers. The way I told you to memorize them is to write any acid and any base, draw their conjugates, write down the numbers, and figure out the direction of the equilibrium. As long as you keep doing that, you'll memorize the whole list because you've used it. You know, I'm greatly against flashcards. I think flashcards are the biggest destroyer of people's education in a real science class. They might not destroy you in a class like Bio 1 or Bio 2, where it's definition-based, but they're going to destroy you here. Because your job, when you're flashing flashcards, right, what you're doing is grabbing something visually and memorizing it. But the questions you get on an exam is not a visual repetition, you know what I mean? It's not a regurgitation of thought, it's a use of thought. So we need a study in the same operation that we're going to be required to do during an exam. And during an exam, you're supposed to use the pKa's, not just memorize the pKa's. So if you're sitting there memorizing them, you're not using them, you're not going to understand how to work them. You draw any acid and any base. Then on the other side, you draw their conjugates. But now I'm asking you to include one other thing. Push the arrows from the base to the acid to show how the proton is being grabbed. That's what Lewis said. And it makes sense from Lewis's perspective. So what Lewis said is that the base is not the proton taker, but the base is the thing that has extra electrons that attacks the acid. The base is the electron donor. And the acid is the electron acceptor. And all three of these things mean the exact same thing. It's just Lewis is the most general. I already told you what I think about this. That the base is electron rich. It's the same kind of a thing that Lewis is saying, except I'm making an idea, I'm adding the idea that the base is electron rich, and the more rich you are with electrons, the worse base you're going to be. I don't mean not the worse base like the less the more angry base you're going to be, the more basic you're going to be, the stronger the base you're going to be. The pK of the acid on this side is -5. What's the pK of the acid on this side? So you look up on the table, you find water, and water is 15.7. 15.7. This reaction is going to go from the smaller number to the bigger number. Which direction does this reaction go in? The answer is to the right. What if I wrote those first? What if I took these and wrote them first? I just did, right here. I wrote them first. Okay. What's the acid on this side? Water. What's the pKa? 15.7. What's the acid on this side? HCl. What's the pK? -5. Which way does it go? To the left. It's saying the same thing. But you know what it's really saying? Here's what it's saying. If I wrote this first, and then I wrote this, you know that this goes in this direction, correct? And if I wrote this first, and then I wrote this one, you know this goes in this direction. You know what this is saying? This is saying that if I had a chair with a tert-butyl axial and I put it in the flask, it's going to flip and become equatorial. And this is saying that if I had a tert-butyl chair that's already equatorial and I put it in the flask, nothing happens because it's already where the thing is going to go. Is that too much to understand? Let me say it in another way. If I took a piece of paper and I burned it, it becomes ashes. If I took ashes, it's not going to become a piece of paper. It stays ashes. If I have this and it's telling me my equilibrium goes that way, then I know that when I put these two in a flask, they'll react. If I put these in a flask and the equilibrium says it's going this way, then when I put these in the flask, they already reacted. They're not going anywhere. This should remind you a little bit of complete molecular, complete ionic, net ionic equations. If you were okay with that in Gen Chem, you do what's called a double displacement. Like AB and CD, you write AD and BC, but it doesn't mean a reaction happens unless you create a solid or something like that, because you could end up canceling everything out and having spectator ions. You see what I mean? When you get a base and an acid, you are asked first to draw the conjugates. But it doesn't mean a reaction will happen. The reaction will only happen if the equilibrium goes in that direction. Please be very aware of this. So, question. Will this reaction happen? Will this reaction right here happen? You're allowed to flip in your book to the table that I provided you. Will that reaction happen? What is the acid on the left side? Which is a -5. There's like very little chance it won't happen. There's only a couple of numbers that are lower than -5. Almost everything else is higher than -5. What's this? That's 9.2. Which way does the reaction happen? This way. Not only does it happen this way, we are going to right now be able to compute an equilibrium constant. What's the equilibrium constant? Here's the calculation. I'm going to give it to you. You're going to use it. And then maybe in a later class I'll prove it. Because I don't like to just say something without proving how it works. But to calculate the equilibrium constant. And do you remember KEQ, KC, and KP from Gen Chem? Right? If I walk up to a Gen Chem student right now and I say, give me the KEQ, they'll be like, that's easy. It's this times this divided by this times this. I was like, yeah, but what's the number? They're like, what's the concentrations? I'm telling you, you don't need concentrations. You could calculate the KEQ without concentrations. How? Here's the formula. 1 times 10 to the change of pKa's. What's the KEQ for this reaction? As long as it's an acid-base reaction, not any reaction, specifically acid-base reaction. It's 1 times 10. What's change in pKa? Final pK minus initial pKa. So what is that? It's approximately 9 minus, anybody following? 9 minus what? 9 minus minus 5, which is 9 plus 5. So what's the KEQ here? 1 times 10 to the 14th power. Isn't that a ridiculously large KEQ? This thing goes not just to the right, it goes completely to the right. This flask could explode. Do you know why the flask could explode? Because delta G is minus RT ln KEQ. You could even calculate how much energy is released. How much energy is released per mole of this? It's minus 2.5 kilojoules, as long as we're doing this at room temperature, times the ln of 1 times 10 to the negative 14th. Now, you know how to take a log of 1 times 10 to the negative 14th, but you don't know how to do an ln of 1 times 10 to the negative 14th. Here's the ln trick. ln of x is the same as saying 2.3 times the log of x. It's a really simple thing. Like, you might look at that and get a little bit worried or confused, like, I don't know what he's talking about. If I asked you, what's the ln of 10 to the third power, instead of that, you write log of 10 to the third power, just multiply the answer by 2.3. And log of 10 to the third power is just 3. So this becomes 3 times 2.3, which is easy. It's like 5 or 6 or something like that, or 7. So what is that? What is this right here? This is negative 2.5 kilojoules multiplied by 2.3 times the log of 10 to the negative 14th. What is, whatever, negative 14th? I meant positive 14th. It's like, that's weird. You know why I wrote negative 14th? Because 10 to the 14th, I'm, for some reason, automatically thinking about the autoionization of water, right? KW, 10 to the negative 14th, right? So my brain just went elsewhere. What's log of 10 to the 14th? 14. So this is negative 2.5 times 2.3 times 14. 2.5 times 2.3, that's approximately 5. I'm just going to call this a 5. And 5 times 14 is what? 5 times 10 is 50, and 5 times 4 is 20. So this is around negative 70 kilojoules per mole. Just to give you a perspective on what that is, ever seen a Bunsen burner red flame? A red flame in a Bunsen burner is around 30 kilojoules per mole. You ever seen a Bunsen burner with a double blue blowtorch sounding conical flame? That's around 50 to 60 kilojoules per mole. So releasing 70 kilojoules per mole is pretty decent explosion. If you have a mole of NH3 gas reacting with a mole of HCl gas, it would violently explode. That's how much higher in energy the reactants are compared to the products. Acid-base reactions happen because of enthalpy. They happen because they're going to lower energy states. And acid-base reactions we're learning first because of the following rule. The fastest reactions are acid-base reactions. They're instantaneous. So as we move through the semester and we learn alkene additions, nucleophilic substitutions, acyl substitutions, and so on, when you see reagents, the first thing you say is, can they do acid-base? Because if they could do acid-base, they won't do anything else. They'll just do acid-base. We're talking about energy. This is the first semester in my life that I've brought in a delta G equation when talking about acid-base. I've never taught it this way before. But I have to. I realized I have to. Why didn't I bring in energy before? Because this reaction is happening because of energy. It's going to the lower energy side. So let me give you another example without doing the math, but just of a reaction going to a lower energy side. And ask you, which is the lower energy side? Let's say you have OH minus reacting with, well, let me write it this way. Let's say you have acetic acid and OH minus. I'm going to write that OH backwards. You have to decide which one's the acid and which one's the base. And then the process is to draw equilibrium arrows. And after the equilibrium arrows, draw the conjugate acid and conjugate base, pushing the correct arrows for the reaction, and tell me which side is the lower energy side. And the side that's the lower energy side is the side the reaction goes to, just like a chair flip. A chair flip goes to the lower energy side, and that's the side that there's more of, right? That's the way that it goes, because it's lower in energy. It falls into that direction. How do you know which side is the lower energy side? The pKa's tell you. Did you capture what I'm saying? Because it's new to you, it might be too much, but how can we say it to make it not too much? We draw the conjugate acid and bases, And then if you find the pK of the acids on both sides and draw an arrow into the direction where it's going, either this way or that way, depending on the numbers, lower to bigger number, the arrow tells you which way the reaction's going, but the reaction's going downhill. So the arrow says which direction is downhill. The arrow tells you which direction is the lower energy side. If right now I draw the conjugates and the arrow goes this way, that means this way goes downhill. If the arrow ended up going this way, then that way is downhill. Do you hear that premise? If that's the carboxylic acid, right? So using my rules, an acid is electron poor and a base is electron rich. Very clearly, this would therefore be the base because there's the electron rich of them. If that's the base, that's the acid. If that's the acid, I'm going to draw a conjugate base. If that's the base, I'm going to draw a conjugate acid. Now I need to put in arrows to indicate how you go from here to there. And you go from here to there, the arrows start at the base. Do you see there's a method to my madness? When we started learning resonance, what was the first type of resonance that I taught you? The negative ABC thing. I try to embed in your brain that electrons, that the arrows start at electrons or the negative region. Do you see it now that the arrows are going to start from here? Over here, one of these lone pairs is going to grab the H. Now you can't make a bond to the H and keep a bond elsewhere, so this bond will go onto the oxygen. Does that make sense? Could you do that? And just because I drew that on that side doesn't mean that when I put these into the flask, it will go this way. It goes to the lower energy side. How do we determine what's the pK of the acids on this side? See how I pluralize that? There's only one acid. It's 4 to 5 because that's a carboxylic acid. This one specifically is acetic acid, so it should be 4.76. But I'm going to just call it 4 to 5. What's the pK of the acid on this side? It's water. 15.7. Which way does the equilibrium go? The answer is to the right, because from about 4.5 to about 15 to 16, how much does it go in this direction? We can't get an exact number, but you know what? I'm going to round this to 5. I'm going to round that to 16. 5 to 16, right? That's the KEQ is 10 to the 11th power. Because 16 minus 5 is 11. 10 to the 11th power. This doesn't go a little bit to the right. It goes 100 billion to the right. There's 100 billion products for every reactant. And now the next story. With a KEQ this big, that means delta G has to be very negative. Are you all hearing this? With a KEQ, this is the most important part. With a KEQ this large, delta G has to be very negative. And now we have to say this. Why is delta G negative? So I'm going to erase some things. And here's what we're going to look at. This side has to be lower in energy than this side. Why? Because it's going to the lower energy side. If the arrow went that way, then you'd say that side is the lower energy side. It's a really simple premise. Whichever way the arrow ends up going is the lower energy side. The arrow points at low energy. So from this side, we've got molecules that are lower in energy than this side, molecules that are bigger in energy, right? Okay. Between these two molecules, though, I'm going to look at the one that's most unstable to make my judgment. So I have a neutral molecule and a negative molecule. I might as well be thinking about the negative molecule. And on this side, I've got a neutral molecule and a negative molecule. I might as well be thinking of the negative molecule. I'm going to explain this a little bit deeper in a second. But when you compare the unstable thing on this side, because remember, nature hates charges and so on. When I look at the unstable thing on this side, that's OH minus. And then I go to this side and I look at the unstable thing on this side, that's COO minus. Do you realize that the unstable thing on this side is more stable than the unstable thing on this side? That this one has a localized negative charge and this one has a resonance stabilized, delocalized negative charge? So saying that we're using the pKs to know which direction the reaction goes is not the reason why it's going that way. And on an exam, you're going to have to do the following. When they draw these things, I'm going to give you the wrong answer. I'm going to tell you what the wrong answer is going to be and what not to say, and then what we should say. They're going to give you these two things. They're not going to draw a box. They'll just give you some acids and base and say, step 1, draw the conjugates. So you will. Step 2, which direction does the reaction go in? And that you just have to give an arrow, this way or this way. And then step 3, explain why it goes that way. And the wrong explanation is by quoting the numbers. Like, using these numbers is what's going to help us figure out where it's going. But if I ask you why, you can't say because that has a bigger number. That's not the explanation. Why has to do with stability of some kind. So the explanation is that the products are more stable, and you say, in this case, it's resonance that is stabilizing the product. So there are 5 effects which stabilize the anion. Did you notice that I underlined that word? 5 effects that stabilize the anion. I could give you another column, another table, that's going to be 5 effects that stabilize the cation. But why do we need to have 2 tables? You realize that negatives and positives are opposite. So if I have some effect that stabilizes a negative, it should be opposite with what it does to the positive. Does that make sense? Like if I say F minus is more stable than O minus because of electronegativity, does that also mean F plus is more stable than O plus? No, it's the opposite. O plus is more stable than F plus because of electropositivity, right? That is, by the way, a term. Electropositive is a real word. Just don't use it in class. I don't know if they know it. I'm serious, but it's a real word. I feel like I taught this right. It's just, it's your first time hearing this, so I don't know, like, people who have heard this before are going to come back and look at this and say, wow, he connected KEQ to delta G and delta G to the 5 effects. We care about 5 effects that stabilize the anion, because if I stabilize one of these anions and lower its energy, then delta G will be negative in that direction, whatever that direction is, and that'll drive my KEQ into that direction, and I know which way the reaction goes. That doesn't mean that's what you're going to use. You're going to use simplicity. To know which way the reaction goes, you're going to cheat by putting pKa's down. See, other professors are not going to tell you to memorize. Why would you memorize the pKa's? Here's what you're going to be expected to do without memorizing the pKa's. They would say, okay, I give you an acid and a base, just draw the conjugate, and use 5 effects to figure out which way it goes. Now, sometimes that's really easy. But sometimes, one effect, if there was an order to it, that would be great, but there is no order to it. Sometimes resonance is more important, sometimes a different effect is more important, and there's no way to guess in which case what's more important. But you know what always works? The pKa's. So if you write the pKa's down, you automatically know which way the reaction goes, and then you just have to pick from the list anything that supports your argument. So what are those 5 effects? In no order. None of these, if I write a first thing, that doesn't mean it's the most important. It's not like the things that we consider with resonance. Remember, in resonance, we considered the octet rule, and then we considered charge location. Octet rule is more important than charge location. This is not the way this list goes. Any of them could be as important. The first thing I choose to write is size of the atom with the charge, and in parentheses, larger is more stabilizing. I am very careful with which words I used here. These are 5 effects that don't stabilize charged particles, but 5 effects which stabilize anions. And then when I said size, I didn't talk about the size of the whole molecule. I talked about the size of the atom that bears the charge. So if we're going to try to understand what specific words I'm using, if I have, let's say, an ethyl group and an S minus, or I have a decalin attached to an S minus, which would you say is the bigger size? The answer is the size is identical. It's not the size of the molecule. It's the size of the atom with the charge. Who's the atom with the charge? Sulfur. Who's the atom with the charge? Sulfur. Sulfur minus is the same size as sulfur minus. Do you hear me? The second thing that can stabilize anions is resonance. Now, could you imagine? We didn't start the course with resonance. I didn't teach you resonance. And right now, when I wrote the word resonance, I would now, at this moment, have to teach you everything I taught you about resonance. You see how that kind of wouldn't work? Like you already needed the resonance experience for weeks in order to be like, okay, I can use resonance. Because otherwise, you might memorize that that has resonance, but other things, resonance. Turns out that this is stabilizing for anions, cations, and radicals. I have to make a mention of that because this list is really the things that stabilize an anion. And larger is more stabilizing for the anion. What if it was a cation? Then larger would be less stabilizing for the cation. Let me give you a quick demonstration of the first effect. The pKa of HF is a 3. The pKa of HI is a -9. Which one of these is a stronger acid? HI, it's got the lower pKa. By how much? But it's stronger by the difference in pKa, but 10 to that power because pKa is log terms. So the difference between 9 and 3 is 12, and 10 to the 12th power, that's how much stronger HI is. It's actually mind-boggling. You know that H3O plus is a strong acid, right? And if you spill some strong acid on yourself, it's going to hurt, right? It's going to burn, right? 1 drop of H3O plus on my skin is going to burn. I'm going to have to go to the hospital. But what's 1 drop of HCl going to do? So the pK of H3O plus, according to me, is a 0. And the pK of HCl is -5. The difference is 5, 10 to the 5th. 1 drop of HCl is 100,000 drops of H3O plus. Kind of puts things into perspective, right? If 1 drop of H3O plus puts me in the hospital, what will a bathtub full of it do? Like, that's crazy, right? How about HBr? HCl is insanity, strong, but HBr is 100 times stronger than HCl. See, the difference is 2. 10 to the 2 is 100. And HI is 1 billion times stronger than H3O plus, 10 to the 9th power. 1 drop of HI is 1 billion drops of H3O plus, which is, what, a swimming pool or something? It's insane. This is a weak acid. This is a super strong acid. The stronger the acid, the more stable the conjugate base. That's the whole conversation right now. So that means that when I dissociate this to H plus and F minus, and I dissociate this completely to H plus and I minus, what's the difference here? The H plus is the same. It's F minus versus I minus, and which one of these are more stable? Before you say it, think the answer's given to you. The answer's on the board. This is a stronger acid. It produces a weaker, deader base. This is already, the answer's already given. It's more stable. You know what we can't use as an argument for why it's more stable? Electronegativity, because that one's more electronegative. You know what we use as an argument for this? Size. I minus has a substantially bigger size than F minus. And the larger size for the atom with the negative charge, the more stabilizing it is. Do you hear what I'm saying? Compare this, by the way. Which of these is more stable? pH4 plus versus NH4 plus. Which of those is more stable? N is over there. P is over there. Do you see P is the larger size? But is it negative? See, this is what stabilizes negatives. But those are positives, so you should flip it. For positives, larger is worse. This is larger, positive's worse. This is more unstable. This one's more stable. This is weaker, that one's stronger. Now, knowing that for the size thing, do you see why for resonance I had to say it stabilizes everything? So if it's cations, it stabilizes. Anions, it stabilizes. You don't have to flip resonance, right? It's stabilizing for everything. It's not like resonance only stabilizes anions. It also stabilizes cations. It also stabilizes radicals. So that's universal. After resonance, we have something called the inductive effect, which I could only describe as a question mark. It's going to be a challenge for me to teach you the inductive effect. So I'm going to kind of not teach it to you yet, and we're going to play the game like this. If you can't find how many effects, there's going to be 5, right? You're going to know size and resonance. You're not going to know this one, but you're going to know the other 2 afterwards, right? So you're going to know 4 out of 5 effects real well. And if you can't find a good argument with any of those 4 out of 5 effects, then the only other answer could be inductive effect. So you'll just say inductive effect. You see what I'm saying? Kind of like the same versus enantiomers, and then there's diastereomers. You know what I mean? Like if it doesn't fit into the same, and if it doesn't fit into the opposite, then it's just other. And then after you're good with that, diastereomers make sense in your mind. The inductive effect is going to make sense in our mind. We just have to kind of leave it alone right now. What are the last 2 effects? And this one is the electronegativity of the atom with the charge. I have nothing to do with it. I'm holding a private class and recording a video. Thank you. I put a sign on my door that said recording in progress. Somebody stole it. It was a nice sign. It was only worth $8, but it's just like, I can't even prevent the knocking. Like, there's just nothing to do. I was thinking of putting like one of those light bulbs that glow red, you know, and say recording, but they'll just unscrew the light bulb or something. Somebody actually stole a light bulb, so if you have groups of me at night, not here, outside, so if you have groups of me at night, the whole hallway's black. Like, you can't see where you're going. Brooklyn's a fun place. Electronegativity of the atom holding the charge. Should I put something in parentheses? Do you know that the more electronegative the atom, the more stable it will be for that negative charge, right? And you should know that that only works with negatives for electronegative, because if I turn it to positives, then it's not the more electronegative. You want the less electronegative, right? Do you understand what I'm saying? Here, look. What is the pKa of H2O? 15.7. What's the pKa of NH3? The answer is 38, right? Not NH4, but NH3, 38. Which of these is the stronger acid? Which? H2O. This is the stronger acid. That means its conjugate base will be weaker. And weaker means more stable. Can we find the reason why it's more stable than NH2 minus? Well, we just found electronegativity. Right? Do you see electronegativity supports my argument? Because O minus is more electronegative than N minus, so that works. Look, go back to this. Go back to this. HI is a stronger acid with a negative, so it's stronger acid than, let's say, HCl, right? They're both strong acids, but HI is stronger. HI is a -9, HCl is a -5, right? You have to very, very carefully pay attention here. All of these are important, but they don't all work. Some will work against you, so you have to pick the right effect. And without pKa's, I'm telling you, you'd be screwed because you're going to be like, how do I know which effect is more important in this case? HI is the stronger acid. That means definitely it leads to the more stable, weaker conjugate base. Why is I minus weaker? Well, you look for size. Compare Cl minus to I minus. Yep, I minus is a bigger size. Check. This wins because of size. Okay? How about resonance? Anything to do with resonance? There's no resonance here. There's no resonance here. Move on. Inductive effect. I don't know what the hell that is. Electronegativity of the atom holding the charge. Which one's more electronegative? This one is. So you know what? Electronegativity is telling me this should be more stable. But we know based on numbers that it's not more stable. So please don't use electronegativity as an argument. I guess in this case, electronegativity doesn't matter. Do you see what I'm saying? Like, and when you pick how would you pick which one? Oh, years of experience. I don't need you to have years of experience. Know the pKa's. Do you see how that's cheat mode? It's like straight up cheat mode, right? That's like when you have the code for the video game. Because look, why is OH more stable? Is it because of size? Did you know in Gen Chem that size increases on the way down, but actually gets smaller to the right? Atoms get bigger to the left, smaller to the right. So which one is bigger, N or O? N is bigger. And bigger is more stable. But we know that's not true between these two things, because we know that OH minus is more stable because it's the conjugate of the stronger acid, because pKa tells us. So that's the job that I need you to do. This is the game that I need you to play. Know the answer already. Because you know pK, we know the answer already. And then we have to explain why. When your professor says explain why it's a stronger acid, you can't say because it's got a lower number. And the reason you can't say it's a stronger acid because it has a lower number is because of language. To me and my colleague organic chemists, if I want to tell my friend that this is the stronger acid, I don't use the words, it's the stronger acid. I use the words, it's got the lower pKa, because it's the same words. The words, it's got a lower pKa, is defining it is a stronger acid, right? So can you imagine if somebody asks you, which is the stronger acid? And you say, water. And they say, why? And you say, because it's got the lower pKa. That's like you saying, it's the stronger acid. Why? Because it's the stronger acid. Do you see how that's not the answer to the question? It's just repeating the question. These are the reasons why. And what's going to be a little tricky in this chapter is that you have to say why it's the stronger acid, not because of itself, but because of how you stabilize the conjugate. It is only a stronger acid because you stabilize what it becomes. And how do you stabilize what it becomes? The 5 effects. Are you hearing what I'm saying? Like, this needs practice because this is tricky for everybody. When I compare these acids, I'm going to tell you which one's stronger, not by comparing them, but by comparing their conjugates. When I compare these acids, when I tell you which one's stronger, I'm going to compare their conjugates. Of course, we already know which one is stronger, so it's a little cheating. And we're going to just use whichever rule helps us in our answer. What's the last thing? So the electronegativity of the atom holding the charge, and more En, more electronegative, is more stabilizing. But not for everything, just for the anion. It's going to be less stabilizing for the cation. And the last thing is hybridization. Hybridization of the atom with the charge. What do I write in parentheses there? For hybridization with the atom, hybridization of the atom with the charge. Now you're going to see a reason for my chapter 1 madness. More S character. Ever heard of something called S character? There was a reason for everything I taught you. Nothing can be forgotten. More S character means more stabilizing. For everything? For everything? No, just for the atom with the negative charge. So maybe I should put a little star over here. For size, it's different for cations. For electronegativity, it's different for cations. For hybridization, it's different for cations. For the inductive effect, it'll also be different for cations. The only thing that's the same is resonance for cations and anions, because resonance just generally stabilizes. But if the size gets bigger, it's good for anions. If the size gets smaller, it's good for cations. More electronegative is good for negative. Less electronegative is good for positive. More S character is good for negative. Less S character is good for positive. Does that make some kind of sense? By the way, for that last one, for the S character game, right? According to the list of pKa's that I gave you, you can have, let's say, an alkane. I'm just going to show one hydrogen on that alkane. You could have an alkene. I'm going to show just one hydrogen on that alkene. And you could have an alkyne. I'm going to show that last hydrogen on the alkyne. And if this gets deprotonated, then it becomes carbon minus. If this gets deprotonated, it becomes this carbon minus. If this gets deprotonated, it becomes this carbon minus. Which of these is most stable? Well, according to the list of pKa's, what's the pK for an Sp3 carbon? It's literally the last thing on the entire pKa table. Should be 50. This one's 50. The alkene is a 40. And let's be careful. It's not the alkene itself, not the double bond. My students get confused in a later chapter. One of the first things that I showed you on the board today was something that somebody asked me because Morelli put it in office hours. Somebody put it in office hours. I'm even sure that it was him. That they show the double bond attacking some acid. Right? We're not going to use 40 as the pK for this. What does 40 mean? 40 doesn't mean ruining the double bond. 40 means deprotonating one of the carbons of the double bond. Do you see that? If anything, what is this double bond reacting like right now? Do you see it's a base? Do you know why it's a base? Because it's reacting with a strong acid and electrons are grabbing the H. Is that starting to make sense out of a picture? Still not, it shouldn't make too much sense. But if we're using bases like this, lone pairs, to grab an H and push electrons off, if I'm using pi bond, it's sort of like that becomes a lone pair somehow in the reaction and pushes the sigma bond off. What is this? What's the pK of this? 25. So which of these is the strongest acid? 50, 40, or 25? 25. If that's the strongest acid, it's only because its conjugate is most stable. So stability, I'm just going to do this. I'm going to write down here, most stable. I was going to say stability increase. I don't want to confuse. Most stable, least stable. And what could be the reason one is more stable? Let's try it. Size of the atom with the charge. Do you think there's a different size of carbon compared to carbon compared to carbon? Not really. Resonance. There's not going to be any resonance here, here, or here. Inductive effect. I don't know what that is. Electronegativity of the atom holding the charge. It's still carbon, carbon, and carbon. Hybridization. S character. What's the hybridization of this? Sp3. 25% S. What's the hybridization of an alkene? Sp2. 33% S. What's the hybridization of Sp? 50% s. Do you remember that p orbitals? Let's think about this carefully. P orbitals look like this. Here's the nucleus, and the p orbital is not near the nucleus at all. The orbital's like way out and way out. The electrons are kept far from home, right? The nucleus is positive. The electrons are negative. If you were an electron, wouldn't you want to be as close to the nucleus as possible? So if you have a p orbital and the electron's in a p orbital, it can't be as stable as if it was in an s orbital, right? So the electrons here, the negative charge, the electrons, are in an orbital that's hybridized, and 75% of it is far from home, and 25% of it is stable close to the nucleus. But here 33% of it is stable close to the nucleus. Here 50% of it is stable close to the nucleus. Do you see as you increase S character, the closer to the nucleus you get, and the more stabilized you are as those negative electrons? Does that make sense? None of these effects are better than any of the other effects. They take turns in different examples, which is why knowing the pKa is the only way. In-class assignment. I like to yell a lot. If I'd whisper, I'd put myself to sleep. You got to be dynamic with it. I said the words in-class assignment, and I didn't give you the assignment. What do you think the assignment is? Draw the conjugates. Tell me which direction the equilibrium goes and why. Do you know which one is the acid and which one's the base? How about this? Do you know which one's the acid? Maybe if you know how to name them. But do you know which one's the base? It's obviously in front of you. Do you see? How? Because the acid's supposed to be neutral or positive, and the base is supposed to be neutral or negative. So if it's neutral, you don't know. But if it's positive, it's an acid, and if it's negative, it's a base. And therefore, I don't know what this is, but this is probably the base. Now, what do you do with the base? You push arrows. How about this? How about this? Hold on. If you don't know how to push arrows, don't do that first. Don't do that first. The first thing you say is, okay, here's my base. And if that's my base, just draw the conjugate acid of this molecule. And if this is the acid, just draw the conjugate base of that. And once you draw it, then fill in the arrow push. Did you get this as your answer? You see how that's the conjugate acid of that negative? And what's the conjugate base of this? It should be this. And you should have done this right here. Did everybody do that? Now what? I'm going to talk about my dog. I don't have a dog. That was a short conversation. I always had professors in college that for some reason like to discuss their dog during the lecture. They would, 10 minutes in, just start talking about their dog for some reason. Any of you have that? You do? It was bizarre. Every philosophy, history professor just have long conversations of how they go upstate and play with their dog. It's it's nice. It's nice to involve us in your life. Okay, what do? You need to figure out which way the reaction's going. Now, you could ignore me, and you could figure out the way the reaction's going by being a master of these effects. But you're going to screw up, no doubt, if you do that. Or you could figure out which way the reaction's going by using pKa and then pick whichever effect helps your argument. So, which way is it going based on pK? What is this? Did you know that's HCN? That's a 10. And what's the acid on this side? Well, this is the conjugate acid of that, and that's a 25. The reaction goes to the right. Which means that this thing here, that is the anion, why am I comparing the anion? Did you tune in? I'm going to compare the anion to the anion because I could only compare anions. Like, I'm not going to compare the neutral to the neutral with 5 effects that stabilize an anion. I should compare an anion to an anion to use 5 effects which stabilize the anions. Is that clear? And like, is there something not clear about that? Not always are you going to have reactions that have an anion and an anion. Sometimes you're going to have a cation and a cation. And the worst is when you have charges on one side and nothing on the other, and then you can't use this in the right way, but we'll discuss those special cases. I need an argument to help me go to the right. Let's start with this. Size of the atom holding the charge. They are negative charges. Which is bigger, this thing over here or that thing over there? The answer is none of them, because it's carbon minus to carbon minus. Do you see? Okay, so that's not the answer. Is resonance the answer? No, because there's no freaking resonance. And even if there was, a triple bond carbon minus is the same as a triple bond carbon minus. There wouldn't be any resonance there. I don't know what that is. Okay. Electronegativity of the atom holding a charge. What is the atom holding a charge? Carbon. Carbon, same electronegativity. Hybridization. What's the hybridization of this carbon? The answer is sp. What's the hybridization of this carbon? Sp. Shit, we have nothing. No, we have something. It goes this way because of the inductive effect. You see, we ran out of reasons, so I'm just throwing in the inductive effect. The inductive effect is a neighboring effect. And what's different about this is not the atom with the charge, but what else is attached to the molecule, right? It's going to be a complicated story because for the inductive effect, there's push and pull effects. There's donating and withdrawing effects. So rather than trying to make sense out of it in a couple of minutes, let's make sense out of everything else. Let's try this again. Tell me which direction the equilibrium goes in after you complete the acid-base reaction, and find the direction of the equilibrium, and then tell me why. By the way, when you're doing this for homework, because I gave you this for homework, right? What I said is pick any acid from the acid column, any base from the base column, draw them. When you pick an acid from the acid column, please look up at the board. When you pick an acid from the acid, or anything from my acids or bases that has an R in it, like RSH, right? Don't write R. Instead, draw a type of R. So what is R? R is a carbon or carbon chain. When you're drawing carboxylic acids, don't draw the same one. Don't train your brain to memorize acetic acid. So if I'm going to do this for homework, I'm going to pick something else. I'll draw like maybe that and then put a carboxylic acid. Just so I see some variation on what carboxylic acids could look like. So I don't train my brain to memorize this picture, but I train my brain to focus and find the group. It's very, very important to be able to find the group. This is, again, the story on flashcards. If you put this on a flashcard and write carboxylic acid, and flash it on the train 10,000 times, your brain will think that is what a carboxylic acid is. Then on an exam, the professor says, what is this? And you're like, I have no idea. That's a carboxylic acid. But that picture doesn't look like this picture. So if you want to put something on flashcards, don't even draw pictures, write words. A carboxylic acid has a carbon with double bond oxygen and single bond OH. Right? And then you'll see that here. Maybe you'll see that here. Okay. What is it? Did you do this? Did everybody do that? Did I accomplish goal number 1 today, which is showing the arrow push for the simplest mechanism we've learned this semester, which is just an arrow push for the acid-base mechanism. The base grabs the H, the 2 arrows, simple. Okay? Which direction is the equilibrium going? Well, what is the pK of this acid? It's 4 to 5, right? If you want to just put any number, just put 4.5. What is the pK of this acid? 3. Which way does this go? That way. Is a good argument resonance? It's a horrible argument. Because this side doesn't have resonance, and this side has resonance, and it's running away from resonance. Do you understand how that's not a good argument at all? What is better about this side? What's better about this side? Start with size of the atom holding the charge. Which is bigger, O minus or F minus? The answer is O minus, right? So this side is better for size. Don't use size as an argument. It's not on this side. It's going to that side. Resonance. Well, this side is better for resonance. Isn't it interesting that this has got lots of things that are good? Inductive effect. Don't know what the hell that is. Electronegativity of the atom holding the charge. Well, this atom holding the charge, by the way, when it comes to resonance, if you're looking at that, the atom holding the charge is not necessarily oxygen. Let me be clear on this. If I showed you this, for example, this is where things are going to start feeling a little complicated. If I show you this, and I ask you about the size of the atom holding the charge, or the electronegativity of the atom holding the charge, it's not nitrogen. Because there's resonance here. And when we want to talk about the atom holding the charge, you should be thinking of the major contributor. And what's a more major contributor? This one or this one? That one, right? So even if you draw this, you have to think about the major contributor. And the major contributor has an oxygen size and an oxygen electronegativity and so on. Over here, it's oxygen compared to oxygen. Not much to think about, right? Size is oxygen, which is bigger than fluorine. Resonance is here because there is no resonance here. I mean, we're comparing the negatives. You could say, isn't there there's no resonance there, it's neutral. Inductive effect, don't know what that is. Electronegativity of the atom holding the charge. The oxygen is the electronegativity, which is a 3.5. That's a 4.0, so this one gets electronegativity. That one's winning for electronegativity. Hybridization of the atom holding the charge. Tricky. The hybridization of this is Sp3. What's the hybridization of that? Do you remember it's not Sp3, it's Sp2? But I'm not going to write down that this is winning for hybridization. And the reason I'm not going to write it down is because why does it have better hybridization? It's because of resonance. Do you see? If resonance leads to a better hybridization, and I claim that it has hybridization, then I'm claiming resonance twice. So don't claim hybridization when it's caused by resonance. Strangely enough, this side has 2 stabilizing effects. This side only has 1 stabilizing effect. But that one is the winner in this case. Could we say the most important effect is the electronegativity of the atom holding charge? Absolutely not. I've already shown you that when it comes to HF versus HI, electronegativity doesn't matter. HI, size matters. So sometimes size matters, sometimes electronegativity matters, sometimes resonance matters. How would you know which one to pick? Easy. I gave you numbers. Now, my numbers are not going to be, my pKa table is not going to give you every single answer for every question they could possibly ask. My pKa table is going to be accurate to like 96, 97%. 3 to 4% of the time, they're going to ask you a question that doesn't go on my pKa table. For example, they might ask you this. They might ask you, complete this acid-base reaction, pH 4 and NH3, right? Please watch, because I need you to know what to do. pH 4 and NH3. Well, first, one of these is the acid, one of these is the base. And because that's positive, I'm going to call that one the acid. So if that's the acid, I'm going to draw its conjugate base, pH 3. And if that's the base, I'm going to draw its conjugate acid, NH4+. Which way does the reaction go? I know NH4+ is a 9.2 pK. You don't have pH 4+ on your pKa table, right? So in that case, This now is one of the 2-3% of the questions that could pop up that I don't have on my pKa table. I still, even knowing that this might pop up, I don't put it on my pKa table. I carefully selected everything that goes on my pKa table. So what do you do with this case? Use the list, because if it's not on my pKa table, it's guaranteed that there's only one real effect that we're worried about. And in this case, the only real effect is size. I could say one detail. When you're comparing size and electronegativity, these are opposites. Notice size increases in the opposite direction of which way electronegativity increases. This way is electronegativity increasing, this way is size increasing. This way is size increasing, this way is electronegativity increasing. Electronegativity and size are opposites, so these will always fight with each other. When does size win and when does electronegativity win? If they're on the same row, size doesn't change much, electronegativity wins. If they're in the same column, electronegativity doesn't change as much as size changes. So for up and down, it's size. For side to side, it's electronegativity. And knowing that, you basically can now answer every question, because either you have the pKas for the difficult questions, or if you don't have the pK, it's a simple question. It's probably one of the effects and only one of them, and just run with that. You see how this top one is a much more difficult thing? Look, if I didn't give you the pKas, look up here. If I didn't give you the pKas, and you were asked which way is the more stable way, I don't think any logical person would say to the left electronegativity when to the right is both size and resonance. Do you see what I'm saying? Like any logical person should say that way. There's just so many more stabilizing effects. But that's the reason I gave you my pKas. To combat those ridiculous questions that only years of experience would give you the answer to. It turns out this is a good place to stop, regardless of being 2 p.m. or not, because I need you to practice the shit out of everything that we've done today. So do that, and then we could go on to the next phase of this chapter. We actually have maybe 1 to 2 more lessons in this chapter, so I think we're going to have to call like extra lessons next week or something.